let's start for just the ideal case, example 1. Consider an LTI system with a frequency response with this frequency response, Hj omega is 1, or let me give you the how we get this formula first. But in this example, we are not going to do it, but I'll mention it. It's just the integration from minus infinity to plus infinity, ht. This is the impulse response of the system, exponential minus j omega t dt. And this is called the Fourier transform. It's different than the Fourier series because this is a more general equation. We call it the Fourier transform of the impulse response. And what we get is the frequency response of the system. In this example, this is given as 1 when omega is between pi over 3 and 5 pi over 12 and 0 otherwise. Do you remember from where did we get this? I think you will find this in the first lecture when you just started talking about Fourier series. And this mainly arises when we have an input of this form to the system with an impulse response ht, then yt will be convolution, j omega t. So yt will be a convolution between those two, which is integral from minus infinity to plus infinity. Let's call this xt. Then we'll just rename the variable to tau, and we do the time reversal and shifting of ht, and it becomes h tau minus t d tau. And if you plug in the ej omega t in here, you'll be able to isolate ej omega t, and then this term will remain. This term will be multiplied by ej omega t. It's not our main focus for today, so it's just a reminder. Anyways, this is called the Fourier transform of the impulse response. And it's in this case is given this way, 1 in this band, or actually those will be 2 bands, one of them in the positive side and the other one in the negative side, and 0 otherwise. If we try to plot this, a variable is omega, the frequency, or it's called also the angular frequency. It's given in radians per second, while we used to have other definition of frequency, which is f, which is given in terms of hertz or seconds to the power minus 1. So when omega is between pi over 3 to 5 pi over 3, let's say this pi over 3, and this is 5 pi over 12, it will take the value of 1 somehow. And then since we have here the absolute value, then this will be satisfied also here on the negative side. So this is minus pi over 3, and this minus 5 pi over 12. Again, it's 1 here also. What kind of filter do we have here? From the last lecture. Anyone? If you wanna answer, just unmute yourself anytime and interrupt. It's okay. This filter is called bandpass filter because those are zeros, obviously. Any value of omega other than those two bands is zero. This is called bandpass filter because and this actually represents a system, because whenever we have at the input of this system a signal with a frequency that lies in one of those two bands, the signal will pass through the system untouched, without nothing will happen to the signal. It will be passed. Otherwise, if the frequency of the signal, the input signal, is anywhere outside those bands, it will be zero. It will be killed. It will not pass at all. That's why also we called an ideal bandpass filter. Ideal. Ideal is because it cuts here at those edges, cut sharply and instantly kills any frequency larger than this value, and kill the frequency like to zero. Nothing will, like whenever the input frequency outside those two bands, nothing will be at the output of the system. So we call it an ideal bandpass filter. Otherwise, the practical bandpass filters will have, the response will be maybe something like this, not like this. Let's say like this. So it will, even the signals outside this band will pass through, but they will be degraded severely outside this band. So if the magnitude is 1 of the input signal, which has a frequency, let's say here, omega, then at the output, we'll have the same signal passing, maybe with addition to some other signals, but the magnitude of the signal will be severely degraded. It will be multiplied by this value, which is, let's say, if this is 1, it's much less than 1. So it will just degrade or suppresses a little bit the signals outside the band. Anyways, in our example, it's an ideal one, and we don't have to deal with those stuff. So this is the impulse, this is the frequency response of the given system, this hj omega. Now the question is, find yt for each of the following inputs. The first input is xt, defined as 1 when t is between -1/2 to 1/2, and also 1 when t is between 1/2 and 3/2.
I've literally been home all day. I have two
sorry.
exams.
Okay. And yeah, the period of this signal will be 2. We are actually here defining a period of this signal, which spans the time from -1/2 to 3/2. So the period will be 3. And the other signal, the other input signal will be 1 plus sine 3 pi divided by 8 t plus pi over 4. What's the frequency of this signal, let's say, or this? What's the frequency of this signal?
Shouldn't it be 1 over 2 pi?
1 over 2 pi. Here we have sine 3 pi divided by 8 times t. So actually the frequency is this one, 3 pi over 8, because the general form is sine omega naught t plus some phase shift, let's say phi.
Would the frequency be pi over 8, or would it be 3 over 16? It's like f.
Oh, that's f. Yeah, but this one is just omega naught is 3 pi over 8, and then we can convert it to f. Omega naught would be 3 pi over 8, and we have omega naught is 2 pi f. Then f will be 3 pi divided by 8 divided by 2 pi. So you will have 6 over 8, right? For f. For f. Okay. I just want to, we now mainly interested in the angular frequency, omega naught, which is 3 pi over 8. And if you remember what we were discussing here when we were talking about the frequency response of this bandpass filter, what do you expect will happen when we have this input at this system? Remember what we have discussed when I was explaining the bandpass, the ideal bandpass filter. What would happen if this was the input of this system? Without doing any math, you should be like, you maybe after doing some examples, you should be able to do it without doing any math. Just guess, give me any guess. If this is the input, this is the input, 1 plus sine something, and this is the system. What will be the output? Remember, the frequency of this signal is 3 pi over 8. And if we look here in the frequency response, 3 pi over 8 will be outside those two bands. Right?
It would just be 0, no?
So yeah, so it will be 0. So because the frequency of this signal is outside the passing band, or outside of the pass band of this signal, of this filter. So it will be zeroed, it will be killed. So if the input of the system is any signal actually that has a frequency outside those two bands, the output will be just 0. And if it's inside this band, it will pass without even, the scaling here is 1, so it will not be affected at all. But because this is only correct because it's ideal bandpass filter, so we have here one perfect one. But in practice, it will be different. It will not be always 1, or it will be very close to 1. in practice. So I just want to, like, you should be able, like, you should do these kind whenever you have time. I mean, this kind of, like, try to expect what will happen if this is the input. And this is the behavior of the system is completely described by this figure. And you can also see this by, if we move this is the time domain. If we move it to frequency domain, what we will see? The sign, what's the frequency or the Fourier series coefficients of the sine? They'll be two impulses, one of them like this, one of them like this, right? And this is the k omega, and this one is omega, or k omega naught. This omega naught, this minus omega naught, and so it will be two impulses. If we look at this one and compare to the frequency response, those impulses will be outside those bands. So if we multiply, because you know that, let me write it somewhere. We usually, to get the output in time domain, we do convolution between the input and the impulse response. In frequency domain, we just do multiplication. Let's say this one has AK coefficients and this one has BK coefficients. We just multiply them. Those are actually the AK of the input. So if we multiply this one with this one, the result will be 0. Anyways, we'll solve it in the mathematical way, but it's good to have a look at what you have before starting with the math. So we'll start by A. Xt is just 1. It's always 1 between -1/2 to 3/2, and otherwise it will be 0 outside this. So the period will be, as we said here, will be 2. And how to find the output when this signal is the input. And we know that the system is LTI. Remember that for an LTI system, let's say this xt, which is periodic. Let me remove the equal sign. It's periodic. If it goes into an LTI system, the output yt will be, if we want to write it in terms of a Fourier series, it will be, and also let's say the coefficients of this xt are ak, then the output will be written as ak, the impulse response, the frequency response of the system, times xt itself. Or, we get the coefficient of xt, but since this is the Fourier series representation, it's times jk omega naught t. But those are actually the coefficients of yt. Let's call them bk. So So as I said before, in time domain, we used to do, let's say this HT, we used to do a convolution to get YT. We do a convolution between the input and the impulse response, we get the YT. In frequency domain, we have AK, which represent XT in the frequency domain, and we have the frequency response. We just multiply them, and we get YT, or we get BK, which completely represent YT, right? Because once we get BK, we can move to YT, because we know that YT can be represented this way as a Fourier series. It's just once we get BK, we just do the summation BK times exponential JK omega naught T. So we have this relation. If we have a periodic input, we have the frequency response. We know the output will look like this. Okay, so let me write it here separately. The output will be summation minus infinity to plus infinity over K. AK, those are the frequencies, Fourier series coefficients of the input XT times the impulse, the frequency response of the system times exponential JK omega naught T. This one is just because this is the harmonics. Those are the harmonics. Because we are representing YT in terms of Fourier series, which is a summation of scaled harmonics. The scaling now, because the system is LTI, the scaling now is just a multiplication between the coefficient of the input and the frequency response of the system. Now, in this question, this is given. We just need to find this, right? So you need to know this, and you need to know how to find the coefficients for a given signal. So let's find the coefficients of this signal given by this equation, this piecewise equation. Find AK for XT, let's say, Fourier series coefficients of XT. And we have this analysis equation. AK is 1 divided by the fundamental period of the signal, integration over 1 period of the signal, then XT exponential minus JK omega naught T dt. XT was given by just 1 between minus 1/2 till 3/2. So both of these branches are 1 and 1. So, and also the period is 2. So 1/2 integration over, let's say, from 0 to 2. And XT will be 1 exponential minus JK omega naught T dt. Omega naught is, let me write it here. Omega naught is 2 pi over T naught, which is pi. Yeah, which is pi. So we can write this one as here as pi. Okay. This integral is simple. Half times 1 divided by minus JK pi. I write it pi this time instead of omega naught. And then exponential minus JK pi T between 0 and 2. which is 1/2 or minus 1/2 times 1 over jk pi times exponential minus jk pi 2 times 2 minus exponential minus jk pi times 0. We know that this one is equals 1. This one equals 1. What's the value of this term? What's the value of this term? Either you don't know or it's too simple to answer. Okay, using Euler's formula, this can be written as cosine minus k pi, I'll keep the order, k pi 2 plus j sine minus k pi times 2, which is cosine is an even function, so cosine x equals cosine minus x. So this terms is cosine. Let's rearrange those for 2k pi. And then sine is an odd function, so we can move this sign outside. So it's minus j sine 2k pi. Now, what's the value of those two?
Sine of 2 pi k should be 0. Or no.
Yes. Yeah, the sine is 0. The cosine is 1. So this one is 1. And we have 1 minus 1. So AK equals, let me write it again, jk pi times 1 minus 1, which is 0. But we are not sure yet if this also applies, like from this equation. Yeah, from this equation, we cannot tell if this applies to the case when k equals 0, right? When k equals 0, we will get 0 divided by 0, right? Because for any k, this term will be 0. Yes, it's 1 minus 1, it's 0. But when k is 0, we'll have 0 here also. So we'll get 0 divided by 0. So AK here is when for k not equal 0. We need to check the case when k equals 0 separately. So for k equals 0, A0 will be 1 divided by T naught integration over 1 period xt, and then exponential minus j k is 0 omega naught t dt, and this one is 1. So it's just the average value of the signal. 1 over 2, 0 to 2, 1 dt, which is t squared sorry, not t squared, which is t between 0 and 2, which will be just 1. It will be 2 minus 0 divided by 2. So on. So we have AK equals 0, or let me start by k equals 0. So 1 when k equals 0, and 0 when k is not 0. Now, what's remaining is just to multiply it by the impulse response and do this summation. Multiply by the impulse response, and then we will get this BK, what we call BK, the coefficients of YT, and then we represent YT in terms of Fourier series by just multiplying the coefficients by the harmonics, and we'll get Fourier series representation of YT. Let me rewrite it here. YT is summation from k equals minus infinity to plus infinity of, let's say, BK times exponential minus plus jk omega naught t. But BK, because the system is LTI and the signal xt is periodic, then BK is AK times HJ omega. And omega is just K omega naught. So let me substitute this in here. Then YT will be summation k equals minus infinity to plus infinity. Let me write it AK this time, and then HJ K omega naught exponential minus J plus J K omega naught T. Now AK is only 1 when k equals 0 and 0 otherwise. So this will be just equals, let me write it in terms of just A. When A 0, when we have A 0 or k equals 0, we'll have, let me write like this, 1 times HJ, and then here also k equals 1 omega naught exponential J k equals 1 omega naught T. This term is when k equals 0, and then any other k will result in 0. So this is when k is not 0. What we have here is just, let me also substitute the value of omega naught, which was pi. We have HJ omega naught exponential J pi T, and HJ omega naught sorry, I did a mistake. K here is not 1, right? We're using k equals 0 here, so this is 0 and this is 0, right? Is that right? Yeah. So we this term is when k equals 0. So those are multiplied by 0, those are multiplied by 0. So everything will be, so we'll have this one, let's say, times h at 0 times 1, because this exponential will be 1. So what's the value of h at 0? We go back to the definition of the frequency response here. This is the frequency response hj omega, and it's 1 in those two bands and 0 otherwise. So at 0, it will be 0, right? At 0, it will be 0. So because we are outside of those two bands, and if you substitute also in this equation, you will be outside this range. So h at 0 is 0, which is 1 times 0 times 1, which is 0. So the output is 0. When the input was given by that equation, which is 1, 1 minus 1/2, 1/2, and 1/2 to 3/2. When the input is this, and we have that given bandpass filter, the output will be 0. Which is mainly because the frequency of this signal was omega naught. Yeah, here. The frequency of this signal is pi, which is, if we look here, it's outside outside those two bands, outside this band to the right here. So the response at this frequency will be 0, and this frequency will be filtered out. It will not pass. So xt will not pass, and the output will be 0. Let's look at the second input signal, xt, which was given by 1 plus sine 3 pi divided by 8t plus pi divided by 4. 3 pi divided by 8t plus pi divided by 4. Again, as we did before, the output will be yt summation plus infinity ak hj k omega naught exponential j k omega naught t. This is given. We need to find this. This is the Fourier series coefficients of the input, ak. And how to find the Fourier series coefficients of this signal. We can do using this equation. This would be 1 plus sine t pi over 8 t plus pi over 4 exponential minus j k omega naught t dt. But this will be very long, and we need to use by parts and with some other techniques to be able to find this integral. And you shouldn't even try doing this in the exam, because it will take a lot of time. You will lose time. if not making a lot of mistakes and not being able to find the integral. You shouldn't, whenever you see sinusoidal signals in the input, you shouldn't look at this at all. Directly apply the Euler's formula. Let me do it here. Directly apply the Euler's formula, rewrite this one in terms of exponentials, and your life will be much easier. And you'll reach AK much easier, much faster than this one, than this path or route. Using Euler's, xt will be given as 1 plus the sign will be exponential everything inside times j, so j times everything inside this sign, the 3 pi divided by 8t plus pi over 4 minus exponential minus j 3 pi over 8 plus pi over 4 divided by 2j. Okay. Then let's just rewrite it a little bit, simplify it a little bit. 1 plus 1 over 2j. Yeah, it's better to split this exponential. Split this exponential because we know, or we might be able to find the value of exponential j pi over 4. So 1 divided by 2j times exponential j 3 pi divided by 8t times exponential j pi over 4 minus exponential minus j 3 pi over 8t exponential minus j pi over 4. Let me distribute this term. So 1 plus exponential j pi over 4 divided by 2j times exponential j 3 pi divided by 8t minus exponential minus j pi over 4 divided by 2j exponential minus j 3 pi over 8t. And now you should be able to see the coefficients of xt. Do you see them? Not yet. Let me simplify it a little bit, or let's just substitute or replace this one by omega naught because omega naught was 3 pi over 8, right? The frequency of this signal is this 3 pi over 8. So maybe if we write it in terms of omega naught will be, we can see it easier. And also I write this one in terms of omega naught. 1 times exponential j times 0 times omega naught t plus this the same thing here, ej pi over 4 divided by 2j times exponential j times 1 times omega naught times t plus minus exponential minus j pi over 4 divided by 2j exponential j minus 1 omega naught t. And can you see the coefficients now? And those are the coefficients of this signal. Just by using Euler's formula, writing the sign in terms of exponentials and simplifying a little bit, we found the coefficients of this signal directly without doing any integration. Here k equals 0, so this exponential will be 1, and it's scaled by 1, so a0, this is a0 equals 1. K equals 1, we have this is a1, and then when k equals minus 1, this is a minus 1, right? Let me write them here. AK, the coefficients of the given signal xt are 1 when k equals 0, and then exponential j pi over 4 divided by 2j when k equals 1, and then minus exponential j pi over 4 divided by 2j when k equals minus 1, and then 0 otherwise. This one is minus here. So this is AK. We'll do the same thing as we did in the previous example to find the, let's say, the BKs, the coefficients of the output. The output YT has those coefficients, which are given by AK, H, J, K, omega naught, right? So now we have AK, we need to evaluate H, or the frequency response of the system at K omega naught, and to find the Fourier series representation of the output, we just do the summation plus infinity of BK exponential JK omega naught T, which is minus infinity to plus infinity AK H JK omega naught exponential JK omega naught T. This is K. And now we have only three terms in this summation. Otherwise, it will be just 0. So when k equals 0, we get 1 times h at 0 times exponential j 0 omega naught t plus, this is when k equals 0. Then k equals 1, we have a1 is exponential j pi divided by 4 divided by 2j, and then h j 1 omega naught exponential j 1 omega naught t, and this one is when k equals 1, plus the last term is This is minus, right? Yeah. So minus now. Minus exponential minus j pi over 4 divided by 2j h j minus 1 omega naught exponential j minus 1 omega naught t. Now we need to find the values of h at each one of those values with the impulse response. We know that h0 is 0, right? From the previous example, and we can see it also from the definition of the frequency response of the system. Omega, when omega equals 0, we have 0 here. So this one will be 0. This one is 0. Now hj omega naught. Omega naught is we said that. Let me write it again somewhere. Omega naught is 3 pi over 8 3 pi over 8. Actually, this one 3 pi over 8 is within this range, right? 3 pi over 8 is within this range. So at the beginning of this workshop, we said it will be outside and then the signal will not pass. That was not correct. 3 pi over 8 actually is within this range. So the signal will pass. And the frequency response value at this frequency at 3 pi over 8 is 1. So this term and this term will be 1. This one will be 1, and this one will be 1. So we'll have, let me remove this. So we'll have this term is 0. This one is exponential j pi over 4 divided by 2j. The h is 1, so the only remaining term is exponential j omega naught t, exponential j. Let me also substitute the value of omega naught, which is 3 pi over 8 t minus exponential minus j pi over 4 divided by 2j times this h is 1, so times exponential minus j 3 pi over 8 t, and using the inverse Euler's formula, this is a sine, right? Let me rewrite it to see it in a better way. Exponential j pi over 4 times this one will be exponential j times 3 pi over 8 t plus pi over 4 minus exponential minus j 3 pi over 8 t plus pi over 4 divided by 2j, which is sine this thing is 3 pi divided by 8 t plus pi over 4. And this is yt. So the input signal was 1 plus this sine, this sinusoidal signal, 1 plus this, which is, if we plot it, this is the 0 and this is 1. And the signal is like this, something like this. Ouch. Oh. Okay. So it looks like this. This is 1 and this is xt. At the input. At the output, we got this one only, right? At the output. So the input was here, the output shifted to be just sinusoidal around 0. And this component is what we call the DC component. It has a frequency of 0. The frequency of this component is 0. It doesn't have a frequency, it's a DC, so the frequency is 0. Since the frequency is 0 of this part of the signal, then it will not pass because it will fall here, because its frequency is 0, it will fall here, so it will not pass. But the second term of the signal, which is a sinusoidal, which has a frequency that falls here, and it passes. And that's what happened, exactly. What happened. Yeah, the input signal has a DC component because it's shifted along the y-axis, so it has a DC component. It has a non-zero average value. At the output, this DC is removed, and we got only the sine part, this part of the signal allowed to pass, because it falls within the band, the pass band of the filter. This one's outside the pass band of the filter. This is the output. So